trying to see what's going to be this K right there. So all of this is going to contribute to that e to the K. So when you plug in 0 for the t, then this a is going to be that 20. So we know that right off the bat. This 0.85 to the second is going to be our e to the k. Is that how we tried to do that? And so then we can just take the natural log of both sides. And that's going to get us to our k. And when you did that, did we get that? Negative 0.325. We have confirmation on that? Good. Oh, good. Then we have, it's going to be this y will be our 20, we said, and then e to the negative 0.325 t. Very good. All right, same idea. We'll try this second one. I'll pause the video and check some homeworks. So are we hopefully seeing that we want B, or I'll use that same color. We're trying to see that this is going to be our B. So again, when you plug in 0, this 15 is going to be that A. And so we're going to get e to the 0.35 is going to be our B. And when you punch that into your calculator, what did you guys get? 1.419. Say it again. 1.419. 1.419. Is that what we all agreed on? And so then we're going to get y is equal to that 15 times 1.419 to the t. Okay? So let's do one of these decibel problems. So suppose sound A. So sound A is going to be 63 decibels, and we'll say sound B is going to be 51 decibels. And what we want to know is how many times louder, or how many times louder is A than B? How many times louder is A than B? And I think our decibel formula is 10 log of this, whatever the sound intensity is of our particular sound, over some comparison thing that's very, very small that we don't really have to know or remember. So we got to the first group up at the board. Pause this for a moment while we look on it. So I'll give you the kind of short version, and then I can sort of explain why it works the way it does too. So we want to take the 63 minus the 51 to get the difference. There's a 12 decibel difference. Now the shortcut version is that's going to be 10 log of, and it's going to be the intensity level of the louder one over the intensity level of the softer one. Then if we just work with this, we can divide the 10 over, and then when we go 10 to this power equals that, or exponentiate both sides, base 10. Did you catch that? A lesser athlete would not have kept possession of that piece of chalk. So we get to there. And then we can multiply that over, and so we're going to see that the louder noise is going to be this number times as loud as the softer one. So then you just put that in your calculator. Remember, 10 to the first is 10, so this is going to be bigger than 10. Would you get 15.85? Yeah. So it's going to be almost 16 times as loud. So our louder noise, which is only 12 decibels bigger, is, you know, more than 15 times as loud as the softer one. So is that okay? So stay up there because we're going to do another one. So, but the reason for this, and you don't have to work all this out, but I think it's nice to understand where it comes from, is this difference in decibels. Remember, the 63 came from the 10 times the log of the louder one over this comparison loudness, which is very, very soft, minus the 10 logarithm of the softer sound over that same comparison one. So looking at the green side here, we can factor the 10 out, and we then get the difference of those logarithms. And so because with logarithms, our rule is that if you subtract two logarithms, you can condense those into the log of the quotient. And that becomes 10 log of, now this is going to get huge. Here's the first one divided by the second one. And so here, this is the division of these two fractions. So when you divide by this, you multiply by the reciprocal, and we'll cancel those, and you get the log of the louder one over the softer one. So that's the reason it works that way, is because of that property of logarithms there, and that this is a logarithmic scale. So if it helps you to know what's really going on, you're welcome to replicate this. But I'm okay with you kind of shortcutting it and subtracting it to get the difference in the decibels, and then knowing that that's going to be 10 times, because this is just our decibel formula, 10 times log of it, it becomes the intensity level of the louder one over the intensity level of the softer one. Okay? Okay, let's try another one and see if we can make it make sense. So I'm going to destroy the evidence here. Let's say that now we have, we'll call it sound P is going to be, we'll say 81 decibels, and let's say sound Q is going to be, say, 63 decibels. And we want to know how many times louder is P than Q. And see if you can run through that process. Success there, Katrina. We have maximized our space. Or can we squeeze in some more on the margins? Would magnifying glass help as you finish that?
No, I think the marker is a bit too thick right now.
You need a fine point, no, you need a fine point marker, I think. I think the rest of us are going to need binoculars.
Nisha, 81 minus 63 is not
You're
90.
going to take the 10 to the 1.
Yes, it is. It's like,
Does the fraction, how do you change that?
wait.
Okay,
So you're right. Yeah, that's what you use right by for that one.
You type in there, maybe that? Oh, that must be the same as the decimal.
Yeah, I just don't know how to like switch it
I
to
think,
that.
I wonder if it's a format that you're, somewhere it's, oh, that's crazy, I've not seen it before. I don't know, we're gonna have to hunt around.
Yeah. Okay.
Some setting that you got on this, but I don't know where you go.
So there's like A and B.
And if you
stretch it like we did this. Just do that same fraction and try that. Oh, that's strange, I've not seen that before.
Oh, yeah.
I wonder
I mean,
if
it's
you.
giant doesn't see the size of these now, but. Who cares? You can maximize your space if you do that with the entire thing. Why don't you start at the top left? Oh, you can just erase. Yeah. It's not like you're gonna go back and look at it, it's already start. Like, okay, well, I can't read it too, and I'll just go ahead and super smart on it. Someone walks in. I just walked over here when I did like in the movies, you know, and there's that crazy mathematician. Oh, I found the answer. And then someone erases it. Okay, we will. We should do it our turn. It's like not as first on the better team. That's the thing, you just write there. Usually calligraphy stuff doesn't work for me. Really? Yeah, because you're really curly hair. And film works, I just like let it dry and then scrunch it. That's the only thing I found out that works. Are you using product? Sometimes I use like curling, like even conditioner stuff, but I don't do it too often. I think it's more than maybe. I know.
What'd you guys get?
We got 63.095.
63.
Well, 096.
0.096. Times as much. Okay, let me just put that on video here. I think we got that. Okay, so we got an answer of 63.096. So we're going to talk about 6.3, the horizontal stretch and shrink. So this is a horizontal stretch and shrink. And this is by far, I think, the hardest one. It's just counterintuitive. We'll see what we can do with this. We give you our function, f of x, made up function. That's 1, 2, 3, 4. That's going to be a 1. That's going to be a -1. So our made up function is going to look like this: loop above, loop below. So this is our f of x. So what we want to do is consider and compare and contrast y equals f of 2x and y equals f of 1/2 x. And maybe now put some colors to associate with this. So we'll do this one in orange, and we'll talk about this one as being our purple function here. So we saw that when we did the vertical stretch and shrink, when that 2 is outside the function, that bigger number is going to stretch it vertically. It's going to multiply all the y values by 2. Everything becomes twice as tall. And so I think it's only natural when you see this that you think, oh, that 2 inside is going to stretch it horizontally, and that would be wrong. So it does not stretch it horizontally at all. In fact, it shrinks it horizontally. So let's kind of talk about why that is and try to make it make sense so that we can remember it down the road. So one thing to do is, if we know that, well, the 0 isn't going to make any difference. So plugging in 0 here and plugging in 0 here, we're going to get the same thing. So at the point 0, this is going to be unaffected by that fact that that's 2. So we're still going to get to 0. But now we know that f of 1 is going to equal 1. So an x value of 1 on the original function will give us a y value of 1 on the original function. Now, for us to pick a value of x that will cause us to evaluate f of 1, we need to choose an x value that is to what x value, when we plug it in here, and then it gets multiplied by 2, will make us evaluate f of 1/2 or 0.5. So when we plug in a value of 1/2 into this, which I'm going to do as an orange function here, then the 2 times a half, that multiplied by 2 happens before we evaluate it in the f function. So plugging in a 1/2 gets multiplied by 2 becomes 1. We evaluate f of 1, which our graph tells us is 1. So when we plug in an x value of 1/2, we get that same y value of 1 that we got in the original yellow function f of x. With me there? Now we know that in the original yellow function, when we plug in 2 for x, f of 2 is 0. So for us to evaluate f of 2 in this function, we have to choose an x value of, to evaluate f of 2, we need to choose an x value of 1. So if x is 1 here, it gets multiplied by 2. We evaluate f of 2, which we can see from the yellow graph is 0. So an x value of 1 here gives us that same y value of 0. And so it's going to be here. So what we're doing is we're smushing this thing in horizontally. So the yellow function takes a whole horizontal distance of 1 to make that complete loop and make it back to the x-axis. This orange function is going to do that in half that distance. It's completed that full loop already by the time we get to x equals 1. It is shrinking this horizontally by a factor of 1/2. Finally, well, similarly, to evaluate f of 3, we choose here an x value of 1.5 or 3/2. So at 3/2 or 1.5, that's going to be right here. Then when we plug that in, we evaluate and get the same thing in f that would be f of 3, which is going to be that -1. And finally, to evaluate at 4, we're going to choose an x value here of 2. And so that's going to take us to 0. So what we get is something like this. And this is really hard to wrap your mind around because you see a bigger number 2 and you think it's going to stretch it because that's what a big number should do, but in fact it shrinks it by a half. So here's a way that I think of it, and I don't know if this helps you or not. If it does, you can use it. If it isn't, you can just pitch it and try to find some other way. I like to think of this x as being like a time, like it's a measurement of time. And so what you see in the yellow function is it takes us, in whatever time you want to think of that, maybe seconds, it's going to take us 1 second to get up to here, 2 seconds, 3 seconds, 4 seconds. So to complete this complete yellow, to travel this complete path in the yellow is going to take us 4 seconds. And what this is doing is it's speeding up that time. So it's making us travel that path twice as fast. And that's why it's going to condense, because whereas this took 4 seconds or whatever time increment you want to make up, this is going to complete the whole journey twice as fast in 2 seconds. And that's what's causing that kind of compression or shrink horizontally. Okay? So it's counterintuitive. So then what we're going to see in a similar fashion when we draw this purple graph, I'm going to have to extend this, I got a feeling. So let me move that. I'm going to write it as, that was our f of 2x that we see in the orange. And so if we've got 4, there's 5, 6, 7, 8. Then, we're thinking this kind of same way, to get where the yellow function is up here at where it takes an x value of 1 to reach this y value of 1, the x value we're going to plug in here to cause us to evaluate f of 1 is going to be an x value of 2. And so when x is 2, we finally made it to the top of that little mountain there. So it's going to stretch that thing out horizontally. In order to evaluate this at 2, to evaluate in the function f an x value of 2, we need to choose an x value here of 4, because then half of 4 is 2, f of 2 is back to 0, so that's going to take us all the way here, and we have stretched that upper loop all the way out so that it is now twice as long. It's a factor of twice as a horizontal stretch of 2. And similarly, it's going to take us 6 and 8, and we'll stretch that thing out in that way. Okay, so it's like I said, this is where people really struggle. And I think it gets even more confused when, if you look at something that's linear or almost linear, like an absolute value, a horizontal stretch and a vertical shrink are indistinguishable. So to really see what's going on, I think you almost have to look at something that is not linear, like a square root of x function. So let's see, but before we do that, let's maybe do a table. We'll look at what it looks like as a table. Well, no, let's do this. Let's do y equals square root of x. So we'll do that as a parent function. And then let's compare and contrast. We'll go back and look at our 2 square root of x that we saw last time. And then let's compare that to the square root of 2x and see how they compare. And again, what we're looking to is what's going to really happen to our point 0, 0 and what's going to happen to the point 1, 1. So in our parent function, what we see is that 0, 0 is a point on this curve because the square root of 0 is 0. 1, 1 is a point on this curve because the square root of 1 is 1. But it is not linear, so we can't use this idea of, rising 1 and running 1 except for that one point. So after that, it's going to be a different rate of change. So there's our parent function, our square root of x function. So on the orange, we said that this 2, that bigger number 2, is at a vertical stretch or shrink. Stretch. So the bigger number works the way you would expect it to do when it's outside the function. Now, we can only do this idea of, rising and running using this horizontal stretch and shrink idea one time because it's nonlinear. So we can think of starting at 0, 0, we can go up to and over 1, and that is going to be a point on that curve. So that's the point 1, 2. And this was 1, 1 on our original. And let's do, I guess we chose green for the square root of 2x. Now, the 2 inside the function, inside that square root, is that a horizontal stretch or shrink?
Shrink.
It's a shrink. Okay, so, but we can only do this by going up 1 over a half. Okay, we cannot think of that as going, up 1 and over 2 to think of it that way. That won't work. So it's up 1 over a half, and that's a point that's going to be on our curve. Because when we plug in 1/2 for x, 2 times a half is 1, the square root of 1 is 1. Okay, so it's going to look then something like this, which you can see is really hard to distinguish between a vertical stretch and a horizontal shrink. Okay, because you could certainly look at that green function and say, oh, we must have stretched it vertically, but in fact what we did is try to push this over horizontally, and that I think makes it even more confusing. In not very long, we're going to start graphing some trig functions, sine and cosine, and I think there it becomes much more clear. I think that's where most people kind of can sort out the difference between vertical and horizontal stretches and shrinks, because you get a curve that just repeats itself over and over again, and then it's easier to see what happens when you stretch it versus when you shrink it horizontally. But in something like this, it's really hard to tell which that is. Okay? Now, if we go even further towards confusing things here, but hopefully trying to sort it out, if we do a vertical stretch and a horizontal shrink, what we can do is see what happens to that 0.00 and that 0.11. So again, we're going to have that 0.00, but now for only one time, we can rise, we can go up and stretch that. Instead of going up 1, we're going to go up 2. Instead of going over 1, because this is a shrink, we're going to go over a half. Does that make sense? So from this point, we can go up 2 and over a half. And so now you can kind of almost see that that horizontal shrink is kind of having a similar effect to the vertical stretch. So it looks like they're both kind of magnifying the vertical stretch. So that point right there would be 1/2, 2. And you can see that 2 times a half is 1, square root of 1 is 1, 1 times the 2 is 2. And you can only do that one time. You can't repeat that process because it is not a slope.
You can technically rewrite y equals 2 times the square root of 2 to the x as y equals square root of 8 to the x, oh, 8x?
So you're talking about this one?
No, the one that we just did.
Okay, let's come back to this in a minute first, because if I see where you're going, we could here, because the square root of 2 times x could be written as the square root of 2 times the square root of x. So now you can see that this horizontal shrink of a half, you know, that we're condensing this by a half, is the same as a vertical stretch of the square root of 2, which is like 1.4. And so, again, because the square root is not linear, they're not exactly the same, but those are an equivalence there. And so then what you were saying, I think you were right, because I think you said square root of 8.
Square root of 8x.
Yeah, that would, so you could do it one of two ways. You could bring this inside, like you're saying. 2 is the same thing as the square root of 4. And now when they're both in the radical, you can multiply their insides, their radicands, and so that will become the square root of 8x. So yes, now you can see that this stretching has really contributed to a bigger shrink, because now we're shrinking it by 1/8. Or alternatively, you could bring this 2 out. Now this is going to look weird, but it's going to be 2 square root of 2 times the square root of x. And so now here you have magnified the stretch by doing this shrink. But it's not a nice, really easy to conceptualize relationship.
Yeah.
Yeah, but your thinking is good. Yeah, that's good. Questions on that? All right. Well, let me change gears. I'm going to give you a function given as a graph. We'll see what you can do with that. So let's say that here is our parent function right here. It's 1, 1, 2, 3, and I'm going to go, let's maybe go up 2, that will work, and we're going to say our function is going to go up here, across till we're at 2, and then back down again. So this is our f of x. That's what I want for the f of x. So can you graph, first of all, so let's graph y equals 2 f of x, and then we're going to graph y equals f of 2x. Let's start with those before we start pulling 1/2s around. Shall we come up to the board to do this, you think? Are you ready for that, or you want to do it in your notes?
Yeah, probably my notes.
In your notes first? Okay, that sounds good. So I'm going to pause the video so if anybody's doing it, they can give it a try, and then we'll see what we come up with. That'll give me a chance to check Colby's homework. Oops. You want to do that? I'll take that as you're ready. So this is going to be a vertical stretch. So that means everything's going to be twice as tall. So maybe I'll put this over here on a separate axis so I can make it taller. 1, 2, 3, 4. 2, 1, 2, So we're going to still have the same x coordinates, but this is now going to be twice as tall and will be there. So the 2 here does nothing with the x values. They stay as they were, but all the y values get multiplied by 2. And this does nothing with the y values, but condenses or compresses or shrinks the horizontal values. So this took us a -1 to get to here. That's going to be half of that. So that's going to be at -1/2. 0 is still going to be 0. The 3, which was where we got to the end of this horizontal jaunt here, I guess 2 rather. Ooh, I didn't do that right. 1, 2, hold on. So that was to 2. And then ended here at 3. So I had 1, 2, 3. Yep. So now what we're going to get is that's going to be done at 3 halves. So 1 1/2 right here. So we're going to come across and it's going to look something like that. Good to go? So let's then compare and contrast that with y equals 1/2 f of x and y equals f of 1/2 x. Okay, I'll give you a moment. Okay, let's see what we can do here. So the 1/2 f of x is a vertical shrink. So that means everything's going to go up. The y values are going to be half what they were, but the x values stay the same. So at -1, we're still at 0. At 0, we're going to be half as tall. So now we're up at 1. And this will go across until we get to 2. So we've got that much. And then we'll be back down to 0 there. So there's our vertically shrunk graph of 1/2 f of x. The 1/2 in here is going to actually be a horizontal stretch. So now every x value gets multiplied by 2. So this -1 will now be a -2, and 0 still stays where it is. 2, the end of our plateau here, is now going to be all the way at 4. So we're going to go all the way out here to 4. And as we land this thing, it's going to take another 2 and take us to 6. So there's our horizontally stretched graph. Okay, so let's look at a table of values and see what this is going to do on a table of values, a numerical function. So here is going to be our x and our f of x. So let's say we're going to go -2, -1, 0, 1, and 2. And we'll just make up some random points here, say -3, -1, +1, 0, and 4. So here are the values of our function. And see, can you make a table of values first for x and f of, how challenging do you want to make it? Maybe we'll start out just with f of 2x. And then maybe we'll do x and f of, to make it more interesting, let's go 1/3 x. Okay? Know what we're doing? Need a demonstration? Or are we ready to plunge on in there?
Can we do some?
Yeah, so I'll do the first one with you then. Okay? So we're going to pick values of x. We're going to pick values of x to plug in here. But then once we plug the x in here, it's going to get multiplied by 2. The result after we multiply by 2 has to give us one of these x values that's going to be defined in f. So for example, if I picked, say, if I picked -2 for x, if I tried to say -2 as an x value here, then what I would have to evaluate is 2 times -2 is -4. I'd have to get f of -4. But there is no f of -4. So that means this is not in the domain of this function. So that's not going to be an option.
It would be -1.
It would be a -1 exactly, because if we put in a -1 here, then that's going to get multiplied by 2 to become -2. F of -2 I do have a value for, and that in fact is going to be -3. Does that make sense? Or in your head, what you're doing is you're saying this 2x, you're setting that equal to each of these to see what you have to choose here so that after you multiply it by the 2, it becomes that value that we can evaluate. That kind of makes sense? Right, so Aaron, what's the next one we're going to plug in?
Negative, or 0.
Not
Negative
0, actually.
Oh, 1.
Not 1. So if we want to eventually evaluate an f of negative 1, what value of x do we have to choose?
Negative 0.5.
Yeah, negative 0.5 or negative 1/2. So if we plug in a negative 1/2 in for this x, it's going to get multiplied by 2 and become a negative 1, which now we can run to this table and see that f of negative 1 is in fact this negative 1. Is that okay, Paige? I don't know if that was a squint eyes because of a yawn or squint eyes because you don't know what's going on, you don't agree. Is that okay? All right, Aaron, what's the next one going to be?
Log 0?
Now we're at 0, yes, because 2 times 0 is 0, f of 0 is 1. So as you can see, the zeros are unchanged. So whether it's a horizontal stretch, a vertical stretch, whatever, the 0 is unaffected by the stretching or shrinking, either vertically or horizontally. That point stays fixed. Okay, next one. What's that one going to be? Heidi, what do you get?
1/2.
1/2. Because now 2 times 1/2 is 1. F of 1 is going to be that 0. Okay, and Emily, what's the last one going to be?
1.
1. Because now 2 times 1 is 2. F of 2 is 4. That's going to be our result. Okay. Ready to try it here? Sage, what's your first value of x going to be?
Negative 6.
Yes, because when we plug in negative 6 here, 1/3 times negative 6 is negative 2. F of negative 2 is negative 3. We can evaluate that. Right, just stretching it, right? At this point, if you're imagining a graph, you would have gone over to negative 2 and then plotted this point. Now, going over negative 2 has been stretched. We're going way over to negative 6 and then down to that same point. Okay? Paige, what's the next one?
Next one would be negative 3.
And what's the y value?
Negative, 1, yeah.
Yeah, so it doesn't change. The y value stays the same. Aaron, we okay? All right, and anybody, what's the next one?
0.
0,
1.
and then
3.
3,
0.
and
6. 4.
okay, good to go? All right. How daring do we want to be? So let me say, now we're going to spend another day on this, so it always goes slow on this. So we'll revisit this and do some of the really hard stuff. But let me say that when we have, I'm going to say when factored, y is equal to, we'll say a times f of b times x minus c plus d. So when this stuff inside what's going into the function has been factored, then each of these letters, A, B, C, D, do a specific thing. So the A is going to be a vertical stretch or shrink. So whatever your original y equals f of x is, if that number A is bigger, it's going to stretch it vertically. If that A is smaller, it's going to shrink it. Now, the key is inside here, this has to be factored before this to work. And if this is not factored, we're going to factor it first, as we'll see tomorrow. This, then, is going to be the horizontal stretch or shrink. But you got to remember, this is the one that's counterintuitive. So that means that a bigger B is going to be a shrink, and a smaller B is going to be a stretch. The C is going to be that, as always, that horizontal translation. Horizontal, either translation or shift, whichever way you may have learned that. That's going to be where are you going to move that thing right or left. And the D at the end is going to be your vertical stretch, or vertical shift, or vertical translation. So how are you going to move that thing up or down? And again, with the minus C, it's going to be the opposite of what you see. So if you see a -2, that's going to move it right 2. But the D is going to be the same sign as what you see. A +5 is going to move it up 5. And so we'll talk about some of this stuff next time, and we'll look at some that are starting in factored form and see what we can come up with, and then some that aren't factored, and we'll factor it first, and then look at what those transformations are.
All right, very good.